Let's now get to doing a few examples on testing a hypothesis about a population proportion value. Here we are now on our computer screen. Let's have a look at our example 1. So a sample of 396 cell phone users shows 300 of them are iPhone users at significance level 0.01 is the sample showing strong evidence that proportion of iPhone users is more than 30%. So learning from our general discussion that in a previous video lesson, then immediately this statement, we want to show proportion of iPhone users is more than 30%. So quickly as a scratch work, I realized that we're trying to make a statement P is greater than 30%. So that is the same as saying P is greater than 0.3. So this is throughout our discussion, our general discussion that we've learned from, this is a good place for being our alternative hypothesis. And so in that way, as far as the two hypotheses that we need to identify as our first responsibilities in terms of finding and testing any hypothesis, then H1 is recognized to be P is greater than 0.3. And so further, after we've learned from the general discussion about testing a hypothesis, then once we can identify H1, then H0 comes out easily by simply replacing this inequality that was in H1 with the equal sign. And so now we have our H sub 0, the null hypothesis. So now null hypothesis says the proportion of iPhone user is claimed to be 0.3. And our alternative hypothesis is arguing otherwise. The proportion of iPhone users is above 0.3. This is for the first time I'm introducing this term. And as we finished with our summary of the steps here, I am going to be able to make some explanation. But this kind of test, since the inequality is pointing to the right-hand side, the test we are about to do is being referred to as the right tail test. And now, first step into testing our hypothesis. Again, we want to prove that generally our proportion of iPhone users is above 0.3. And we're trying to, once we're successful proving this, we are rejecting that proportion of iPhone users equal 0.3. Now, to successfully test our hypothesis, let's have a closer look to know better about the sample we have. Back on my computer screen, we are using a sample of 396 cell phone users. And in that sample, we found 300 of them are iPhone users. And so, as far as sample proportion, we use P hat equals 300 out of 396, which is in decimals 0.7576. And of course, the number in our denominator here is the sample size, how big the samples that we use. So our sample size is 396. It is then to understand that even though we have a sample here, but we must constantly realize that this is not the only sample that we can ever find. There are indeed infinitely many other samples out there, provided they are all in the same sample size. And so in that way, the average of all sample proportions, of course, each sample is at sample size 396, but the average of all sample proportion. So now recall about that mu p hat. Mu p hat in our case here is going to be 0.3. And again, allow me to show the explanation of why this mu p hat equals 0.3 at the very end after we finished putting all the steps together. And again, after we know the average of all sample proportions, then among all sample proportion values existing out there, sigma p hat, the average spreading of all sample proportions, is going to be found by 0.3, the value being claimed, multiplied by 1 minus 0.3, and divided all that by the sample size 396. And the entire expression here is being inside a square root. Calculation comes out to be 0.0230. And unless being specified otherwise, normally I would go with a standard deviation sigma p hat value to be in 4 decimal places. So the role of this sigma p hat is to be the average spreading of all sample proportions, in which our sample proportion is one among them. And so now, once we have had sigma p hat being calculated as 0.0230, and recall that this formula came out from those days we study about the central limit theorem. Our sample being one sample among infinitely many other samples, but then relative to the average of all sample proportions, then our sample is going to have a z-score on its own. So z-score, particularly for our sample, I use the symbol, this is an optional symbol that I use, but z-score with a subscript p hat, indicating that I'm calculating the z-score particularly for our sample value that we're calculating here. And so from where our sample value was, 0.7576, subtract 0.3, the average, the center of all, the mean of all sample proportion value, and divide that by sigma p hat, which is the standard deviation of all sample proportion values. So 0.0230 is going in the denominator. Calculation comes out to be 19 point, and a quite long in decimal, 8956, and a lot longer, and being a positive value. But now, unless being specified otherwise, for z-score usually I'll go with 2 decimal places, and in this case we are forced down to positive 19.9. So this is the z-score specifically for our sample relative to the center of all sample proportion value data out there. Now at this point there's a checkpoint to check for consistency, but our z-score is being a positive z-score. So this should be consistent with the fact that back in our alternative hypothesis, we were trying to prove that generally if we picked any sample proportion, it should be above this claim value 0.3. And that's one way how we can see that our sample is carrying a positive z-score. Further, our sample being a positive z-score is also consistent with the fact that our testing procedure that we're doing is a right tail test. Even though at this point I still have not explained what exactly the right tail test means, but we will get there once again as we finalize all the steps and putting all the steps together. After getting the z-score of our sample, the next step, I am going to calculate the probability that among all sample proportions, which I represent by generally a random variable capital P hat with a subscript 396. I want to find a probability that among all sample proportions, I am going to find a sample proportion value anywhere greater than or equal to 0.7576. And another consistency checkpoint right here. But the way how I set up my probability problem here, P in parentheses, and I want to use the right hand side inequality, the inequality that points to the right hand side, to make it consistent with the fact that our test here is being a right tail test. And we are using our sample value. We want our inequality to be greater than or equal to the value here came out from our sample value being 0.7576. Now, to calculate this probability, imagine that if we were on a bell curve, then on a bell curve of all sample proportion values, then maybe a 0.7576 is somewhere, and here we are finding the area according to the way how the inequality is set up, and we're looking for the area shaded to the right hand side of the value 0.7576. And so in that way, we have this probability equal to the probability that on the standard normal distribution, we're looking for a z-score being greater than or equal to 19.9. And whichever comes out from this calculation value, we refer to that value as the p-value of our sample. So in other words, our sample being this value, but it will have a p-value. So any sample that we picked up has a p-value, and this is how we calculate a p-value for the p-value for our sample. And so continuing into this problem. So now at this point, apparently, once we put ourselves into this standard normal distribution setup right here, then we can start running our LS&D program that I have mentioned so many times of how to use it. When LS&D asks for a z-score, we are going to give 19.9. But notice, remind yourself again that LS&D is going to give the area to the left of the bell curve. And so but since this problem is looking for the area shaded to the right hand side, we are going to subtract the answer coming out from LS&D from 1. Now back on our computer screen here with my LS&D program on screen, then with z-score 19.9, and I'm now going to run the LS&D program. The area shaded to the left on the standard normal distribution curve is going to be 1. It's indicating that it's a value that's close enough to 1. And so now subtracting that value from the LS&D from 1, we're now looking at our p-value. It's finally concluded as 0, or usually I write 0.000. To indicate, it's just my style, I want to indicate that this is not an absolute 0, but it's a value that extremely small, close enough to 0, to the point that it's in 4 decimal places. It's already 4 decimal places with all 0 out. So with our p-value, how can we tell if our sample, so because so far we are doing only steps and steps of calculation, different steps of calculation, and we came to this final calculated, what I so-called the p-value. But how can we use that p-value to decide whether or not our sample can be a strong evidence or not? And so remind yourself that back on our computer screen here, how can we tell whether or not our sample can be strong evidence or not? Because ultimately our question is asking, is the sample showing strong evidence? So being strong evidence or not. Now this is the first time we are going to learn how to use this, what's so-called significance level. So with this significance level being given 0.01, I am going to compare our p-value that we previously calculated with this significance level given at 0.01. Comparison clearly shows that our p-value is well below the significance level. And so now this is how we can make the decision about whether we're having strong evidence or not. So since our p-value is below the significance level, that means our sample is strong. This sample value that we collected, it is strong evidence. And what's the ultimate purpose of having a strong evidence? This strong evidence is going to be successful for us to either, we can say, to reject. That's one way we can say we have strong evidence to reject our null hypothesis h sub 0. Or another way we can say we have strong evidence to support our alternative hypothesis h sub 1. And now once again back on the screen here of the computer, the question ultimately is looking for, and it is a yes or no question, is the sample showing strong evidence? And so now apparently we just showed, based on that decision right here, we just showed that our sample is strong evidence. So now ultimately the answer as a yes or no, we're looking at yes. Our sample we're using here is showing strong evidence. All right, so now I am going to be giving as much explanations as I can to explain why the steps for testing our hypothesis in example 1 were carried out as previously shown. So we already learned, and I don't think we need to look again at how we came up with the two hypotheses. So I am going to give my explanation for the steps after we have found our hypotheses. So here I'm just restating our hypothesis that h sub 0, our null hypothesis, was saying p equals 0.3. And our h1, the alternative hypothesis, was saying that the proportion of iPhone users should be generally above 0.3. And currently I am not going to rush into explaining what the right tail test is all about. So all we know for now is that we have two hypotheses. Somebody is claiming in the null hypothesis that the proportion of iPhone users equals 0.3. And the idea now is that we're testing this statement right here. We're testing the statement from the person who claimed that proportion of iPhone users equals 0.3. We're testing for the truthfulness of this null hypothesis. And so for that reason, we are considering our sample. And along with considering our sample, we are suggesting a null hypothesis. And so our sample that we used was, we found 300 iPhone users in a sample of 396 cell phone users. And this sample, according to our calculation step, we came to 0.7576. And the sample size we used was 396. And so, of course, this sample itself is already much above the value being claimed here. And this claim value, so I have to highlight this is only a claim, and I have also explained this many times in our general discussion of the idea of testing a hypothesis. So this value is only a claim, and our work here is to verify, to test whether or not this hypothesis can be anywhere likely to be true or not, or we must be rejecting it. And so, because again we're noticing that our sample proportion here is at value 0.7576 is being quite above 0.3 right here. That's why we are suggesting an alternative hypothesis. P should be generally greater than 0.3. But now I am going to save all that logic for later to explain really in detail. But let's now think about the ideas like this. We pick one sample, and in reality, that's a lot of time how it happens. We only have enough, let's pretend that we only have enough manpower and resources to collect only one sample. And so now once we have collected one sample, and our sample came out from the sample size being 396. And so again, I have to remind anyone looking at this sample that as long as we can pick a sample proportion here, that means there are infinitely many other sample values of the same kind out there. So in this context right here, we're looking at the sample proportion value. And that means, along with what I just said, at sample size 396, we have seen this idea so many times before. There should be infinitely many other sample proportion values out there. So our sample value here we have is not the only one. And so in that way, back in our study about the sampling distribution of a sample proportion of a proportion value, then I define that random variable capital P hat 396 right here is to represent the proportion, because there are so many values to the point that we have to define a variable to generally represent the proportion of iPhone users in a sample, in any sample of 396 cell phone users. Then in that way, once we realize there are infinitely many sample proportion values existing out there, then definitely there has to be a center of all these sample proportion values. And so I notate that center being mu p hat, and truly this center of all p hat values is the mean, the population mean of all sample proportion values out there. Recall for yourself the idea that the entire distribution of all sample proportion values is a population. And that's why this average of all sample proportion values is a population mean value. But now, at this point, really, we don't know what mu p hat is. But so now from the central limit theorem, that we previously learned, then mu p hat is proven to always equals to p. So I need to recall anybody viewing this video about that. Mu p hat always equals p. And in this case, we really don't know what p value is, but somebody already made the claim right here. Somebody already made a claim, the person that we're testing, this claim that the proportion of iPhone users equals 0.3. And so now here's the logic. If the statement in h sub 0 was true, okay, and I have to underline that the logic here is that we really don't know if it's true or not, but right now let's start out by saying what if it was true? What if the h sub 0 statement was true? If h sub 0 statement was true, then as a consequence, the central limit theorem, as I briefly mentioned, the central limit theorem would take that. If this was true, then of course the average or the mean of all sample proportion values, which we knew from the central limit theorem, equals p. But now p is at the moment accepted. That's why I'm saying if we're letting h sub 0 being true, then mu p hat would consequently be equal to 0.3. And that's why we had this step back in our step-by-step instruction like that. So anytime you have a claim, anytime we have a claim to test, the claim value, or the value being claimed in the null hypothesis will consequently become the center of all sample proportion values, or the mu p hat. This is, or as well, we can also understand that this is the average, the mean of all sample proportion value. And then further, because we have infinitely many sample proportion values out there, our sample proportion value we have here is only one among them. And so in that way, of course, once we've had center, this is center. So once we've had center of this population of sample proportion values, then every sample proportion value makes some distance away, makes some deviation away from our center. And that's why standard deviation is the average of all spreading, is the average of spreading, the average of how all proportion values, all sample proportion values being deviated away from this center. And so central limit theorem, again, we've learned that sigma p hat can be calculated by p times 1 minus p divided by the sample size, and put all that expression inside the square root. And so in that way, look at the consequence here. So once we are currently we're saying that if h sub 0, assuming h sub 0 was true, that means for now let's accept this to be true for here, then consequently it already became that claim value in our h0 statement already became our center of all sample proportion values. And also we can use that value to substitute into our standard deviation of p hat calculation here. So that means consequently we're looking at sigma p hat equals square root of 0.3 times 1 minus 0.3 divided by 396. And this is the reason why we had that step as being shown in our step-by-step instruction of the problem. And so our calculation from the step-by-step instruction showed that we had average spreading of all sample proportion values being 0.0230. And so once again, as a reminder, this value, the impact of this result here, this is the average spreading, or the average spread of all sample proportion values away from this center. And so now, again, our sample proportion value here is only one sample value among infinitely many sample proportion values out there. But now we already had center, or the mean of all sample proportion values, as well as we also had, standard deviation of all sample proportion values. This is the sigma p hat right here that we already calculated. And so having mean and standard deviation, now we can always calculate the z-score for our particular sample. And so using a subscript p hat here is only an optional thing, but the idea now is that I am calculating the z-score of my particular sample to be relative to the center. And so the way calculating z-score, again, the value itself, the value of the sample itself, where it stands, 0.7576. Subtract the mean of the data. Our data here is currently the entire sampling distribution of all sample proportion values. So our particular sample proportion, subtract the average or the mean of all sample proportion values out there and divide that by the standard deviation. At this point, calculating z-score is just that work, hopefully familiar enough to anyone viewing this video at this point right here, because we have learned that throughout the entire quarter. So our standard deviation here is 0.0230. And so calculation came out to be 19.9, and I actually explained earlier in our step-by-step instruction that the actual calculation came out to a much longer decimal expansion, but unless being specified otherwise, then normally I would go with just 2 decimal places. And in our case here, for this z-score over here, rounding down to 2 decimal places is forcing us to round down to only 1 decimal here. And further, this is a positive z-score. Okay. So now, at this point, we understand the consequence of making a claim. Anyone making a claim right here, then if we let that claim being true, then that claim value in the null hypothesis statement consequently become the center of all sampling values. And also average spread of all sample proportion values can also be found by the formula by the formula proven in the central limit theorem. And so once having center and average spread, then we can always find the z-score for our particular sample. And here we are testing a hypothesis using our sample as a sample proportion. And so the z-score for our sample here, I use the optional. So sometimes I might skip, but here I feel it's best to just indicate as clear as possible. So z with a subscript p hat, the subscript p hat is only optional, but it's making it clear that this is the z-score of our particular sample. Now, on the other hand, our sample is one sample among all the samples of size 396 each. And so, or in other words, our sample is currently at sample size 396. So with this sample size that we are currently using, I am going to multiply my sample size 396 with 0.3. So notice that this 0.3 came out from the claim that we're currently accepting. So currently we're accepting that 0.3 is the actual proportion of iPhone users. And so this product came out as final calculation to be 118.8, which is a number much greater than 10. Then again, with the sample size that I'm currently using, at that sample size we're using, then multiplying 396 with 1 minus 0.3. And again, this value 0.3 came straight out from the value being claimed in our null hypothesis. And currently we are relying on this. We're accepting this value to be our population proportion value for iPhone users. And so 396 times multiplied with quantity 1 minus 0.3 equals to 277.2, which is another value that's much greater than 10. But now, what's good about doing these two multiplication work right here? We've learned that according to the central limit theorem, then as long as these two requirements are being passed, our sample size being 396, and we use this back then as a requirement to check whether or not all of our sample proportions can be placed on a bell curve. And so here, once again, I'm using this as looking right at our sample size. That's what we're using, and consequently combined together with the fact that we're currently accepting, because we're accepting 0.3 to be our population proportion value of all iPhone users, then consequently we are going to pass that requirement, and now we're proving that all sample proportion values of size 396 can be placed on a normal distribution, or can be placed on a bell curve, which takes center at 0.3 and standard deviation point 0230 as we have calculated previously. So this came from our mu p hat, and this came out from our sigma p hat value. And this is the reason why when we later on, according to the steps that I was showing previously, then when we were calculating the p-value, then I was setting up, and I still have not explained why we were setting up this particular probability problem. But for now, let's say once I set it up, find the probability of p hat subscript 396 to be greater than or equal to 0.7576. Then part of my explanation was that I drew a picture on the bell curve. So this is the reason why we just now proved that all of our sample proportion values at size 396, including the sample that we are currently using, we can place them all on a bell curve. And that's why we can do this calculation as a bell curve problem. And so, of course, according to the statements right now, then we're looking at an area shaded to the right-hand side on a bell curve from wherever 0.7576 is. This bell curve has, now we're clear that this bell curve has center being 0.3, and the sigma p hat for this, the standard deviation on this bell curve, sigma p hat equals 0.0230. Okay, and of course any value on this line right here is a value of the random variable capital P hat 396. And so consequently, the calculation here can be done by making it equal to the probability on the standard normal distribution bell curve. That's where we're looking for z-score being anywhere greater than or equals to 19.9. And the work came out for the calculation as 1 minus the answer coming out from the LS&D program with z-score 19.9. So our p-value was calculated to be some value so small that nearly zero, even in 4 decimal places, it's all just 0. And that's the explanation of why we were able to proceed the calculation for the p-value calculation based on the bell curve, because the bell curve came out consequently as what we were proven based on our sample size and based on what we're currently accepting as our truthful population proportion value of iPhone users. So at this point, it is vital to understand that any of the calculation work here came out as a consequence of relying on h sub 0 being true. And so what if h sub 0 wasn't true? Then eventually the calculation here will have to hit some conflict, and I'm about to give that next pieces of those next pieces of explanations. All right, so let's look again at the bell curve a little more carefully. We've learned a while ago that in any data set, in any data, those values having z-score inside of the interval from -2 to 2 are being regarded as the usual values. And so, of course, those values that having z-score either above 2 or below -2, indicating being 2 standard deviations above mean, or 2 standard deviations below mean those values are being referred to as the unusual values. And the reason for this is that according to the empirical rules on a bell curve, a normal distribution, where mean value is always known to be right in the middle of the bell curve, then there are about, we've learned from the empirical rules, and here since we don't need to pull out a calculator and do formal calculation, and so empirically speaking, there are about 95% of data being located inside of the interval anywhere from -2 to 2 for z-score, the interval of from 2 standard deviations below mean to 2 standard deviations above mean. And so in that way, according to the empirical rules, then there's only 5%, there's only 5% of area on the bell curve being outside, and that area is being equally distributed on the 2 little tail here. That means now if I'm making a shading, this little tail is only a 2.5%. There's only a 2.5% of those values being above z-score 2, or there's only a 2.5% of those values falling below z-score -2. And having low probability like that, low percentage like that, that's why they are those values being referred to as the unusual values. Now, noticing how the area of all the usual values are being located right in the middle as a big fat area in the middle of the bell curve, and the area, the 2 areas where the unusual values are being located in the 2 sided tails, 2 squeezed tails on the bell curve right here, to the left and to the right. Then we can extend that concept further to a generality on the bell curve. That now, generally on any bell curve, with the mean right in the middle, then we can always have, there's always a big fat area in the middle. And now in this generality, I refer to the big fat area as the common area. It's the common area, or this area is where we have all the common values. So all the values in here are referred to as common values. Okay, as the terminologies. And outside, equivalent to these 2, the outside areas, then outside of the common area now, we can refer to these 2 either to the left, that area extremely to the left, or that area to the right hand side here in the tail. We can refer to these as the values in here are the unlikely value, because due to the fact that they are located in the areas where it is very low probability to be in there. So any value has low probability to be in either the extreme end on the left or to be in the extreme end on the right end. And so these unlikely values are at low probabilities. And the area itself, we refer to them as the unlikely area, where we have unlikely values. And now, relating to the empirical rule that we just briefly recall, then 2.5 being considered as a low probability is only to a good majority of people out there. But then, for some other people, a probability being 2.5 is still not small enough to be considered as unusual or unlikely values. And so in a general idea here, then the area, the unlikely area here, each one of the unlikely area here can be even smaller than 2.5% to be regarded as the unlikely values, indicating that or being low probability. And so that's why in our problem of testing a hypothesis, then significance level notated as the alpha symbol can sometimes be even given smaller than these commonly used value 2.5% and 2.5%. But significance level now in this concept of being the common area or the unlikely area, then the significance level in a testing hypothesis problem is how much area being to the right outside of the common area value, or how much unlikely area being to the left outside of the common area values. The significance level is in other words, the probability of how much probability, how low the probability that a value can possibly fall into this unlikely area or fall into the left side unlikely area. And now specifically in our testing hypothesis problem in example 1, looking at our computer screen here, we have a significance level given to be 0.01. So our alpha equals 0.01 or 1%. But that means this right tail, the little tail outside of our common area value right here. So this right tail is being as big as 0.01. And the very same significance level being 0.01 in our problem means this left tail, the unlikely area, the area outside of common area, but being to the left of the bell curve, is also 0.01. So in other words, significance level is a way to indicate how big the amount of area, the amount of unlikely area outside of the common area. And now further, in our testing hypothesis problem of example 1, we already understood how all samples can be found, all sample proportion values can be found on a bell curve. And the value claimed in the null hypothesis was consequently the center on the bell curve. Then with our sample proportion value as a proportion 300 out of 396, and being in calculated decimal, we got 0.7576. We knew for sure that this value, this sample proportion value, is above the value being claimed in our null hypothesis, or graphically speaking, this value should stand somewhere to the right hand side on this bell curve here. However, we want to find out further whether or not this sample proportion is still inside of the common area here, or it would fall into this unlikely area, being only as small as 0.01. And I will explain the reason why we want to know it. I will put all those logics together about why we're interested in finding out whether our sample will not only be greater than the value being claimed in the center of the bell curve, but also fall into the unlikely area. I will give that explanation at the very end. But here, since we're interested in finding out whether our sample can fall into the right tail, the tail that appears to the right and outside of the common area. That is the reason why this problem is being regarded as the right tail test. So being a right tail test means from where our sample is. Of course, being already greater than the value claimed in the center, but we further want to test whether or not our sample will also fall into the right tail, the tail on the right hand side of the bell curve that's outside of the common area. And that's what it means by being a right tail test. All right, and so now among the steps that I have addressed earlier in this video, then there was a step where I was showing the calculation of the p-value for our sample. And so the p-value as a mathematical setup, it is the probability where we're looking for among all sample proportions of size 396, we're looking for the sample proportion value being greater than or equal to 0.7576. And since now, up to this point, after seeing a lot of explanations, then clearly this problem is a problem on the bell curve. And so being on the bell curve, then this probability on our current bell curve or sampling proportions of size 396 is on the bell curve. We're centered at 0.3, and this probability is equivalent to the area point shaded to the right hand side of 0.7576. And so the calculation for that is equal to the calculated value on the standard normal distribution where z-score is greater than or equal to 19.9, positive z-score 19.9. So, and to remind yourself that 19.9 is the z-score we already calculated specifically for our sample proportion value. And so we came to our final p-value being 0.000. Okay, and I further pointed out that with our current calculated p-value being well less than 0.01, the significance level given in the problem. So this is our alpha value right here, the significance level alpha. And so now at this point, what does this mean? Especially how is this connected with the fact I was discussing earlier that we are currently interested in finding out whether or not our sample is still in the common area on the bell curve. So our p hat, is it being 0.7576? Is it inside of the common area or falling into the unlikely area? How is this comparison between the p-value and the significance level given in the problem connected to this explanation that I have had earlier? So here's how it's connected. Now with a brand new bell curve that I'm about to draw here. Allow me to draw the bell curve a lot bigger. Okay, and so on this bell curve we have already been well aware that the center of the bell curve is that claim in the null hypothesis being 0.3. And so right now let's not worry about the common area, but 0.7576. 0.7576 is somewhere, I mean how far it is, that's not really important, but for sure it's somewhere to the right hand side of 0.3 on this current bell curve right here. And so the p-value we have calculated, anyone viewing the video at this point should be well aware about the meaning of this calculation. This probability on this bell curve is graphically the shaded area to the right hand side of 0.7576. So from where our sample is, 0.7576, we have a p-value which is in black, shaded right here. This p-value, and calculated to be a value 0.000. I'm not saying that it's an absolutely zero value, but it's something small enough. That's why it allowed me to still draw some black area that everyone can still see. But this area here is supposed to be, according to the calculation, so small that in 4 decimal places it's a 0. So that is our p-value of the sample, how much area shaded to the right hand side from where our sample stays on the current bell curve, the sampling distribution of all sample proportions, size 396. But then this area, after a direct comparison with the significance level, and of course just now I gave the meaning of the significance level. On this bell curve like this, the significance level is how much area outside of the common area and being shaded to the right hand side. And so in this particular situation, our significance level being 0.01, which is greater than this p-value. So in a way, if I would draw the significance level as a shaded area together with this p-value, then here's how the picture looks. My significance level needs to be how far bigger? That's not important, but I hope now you see the overlapping between the red and the black area. So due to the fact that the black area representing my p-value is being smaller than the red area as my significance level, that means for sure, take a moment and feel free to pause the video to think about it. But that means for sure my sample must fall inside of the red area being referred to as so this area all in red, starting here and to the rest of the bell curve to the right hand side. That is how big the significance level is. So the significance level 0.01 is all that area in red, and our p-value is the area in black. But being the area in black as a direct comparison is once again smaller than the significance level. So meaning if we're drawing that on the picture, then the black area should be contained completely inside. That means as a sample point, then the sample point for our value has to fall being within the unlikely area represented by the significance level on this bell curve. So from this observation, along with my explanation, then we come to an important conclusion here. Our particular sample proportion value, this 0.7576 here, is among the unlikely values. And what I mean unlikely values, the unlikely sample values. Now that our sample proportion value p hat is among the unlikely values, so now we can say that p hat is an unlikely sample value. And this is what making it strong evidence. And making it, I mean making p hat strong evidence. And so ultimately, as I have discussed earlier, strong evidence here is in the purpose to, we can either say to reject h sub 0, or we can also say to support h1, the alternative hypothesis. And now let me explain why is it that as long as we can prove our p hat being an unlikely sample is an unlikely. So as the conclusion I have stated earlier, p hat being an unlikely sample value, then that leads to p hat is being strong evidence. On one hand, to say to reject h sub 0 or to support h1. But ultimately, I would like to give the explanation of why is it that once p hat can be proven to be an unlikely sample value or being among the unlikely sample values, then it leads to the understand that p hat is it can be used as our strong evidence, or p hat is showing strong evidence for us to reject h sub 0 or to support h1. So now we have to look at the bell curve that is the distribution of all sample proportion values of size 396 here. So recall for yourself the meaning of the capital P hat 396. Any value that this random variable takes is a sample proportion out of size 396. And so we started out by looking at the claim saying that proportion of iPhone users equals 0.3. And so in the beginning part of my explanation, I started explaining that what if we let this statement being true? So if h sub 0 was true, so now if h sub 0 was true, meaning this claim, this value 0.3 being claimed in our null hypothesis is now consequently the center of the bell curve. And we spend our time showing that all values of the sample proportions here, all values of our sample proportion can be found in a bell curve like this. And so on this bell curve, if the center truly is what it's claimed to be, then recall that our significance level is only a 0.01 here and a 0.01 there, or we can think of that as a 1% on each tail. That means we can do a quick math here. That's the entire bell curve area is 1 or 100%. There's already 1% of area given to those to that area of those value extremely high or unusually unlikely high, and then there's also another 1% that for those values can be unusually low. And so in that way, the math can easily come out to be there should be 98% of data values that fall in the common area right here. The common area. And so we just now proven that our p hat is in this area. In the unlikely belongs to our p hat belongs to the unlikely area to the right here. So now the logic is as following. If that claim truly is the truth and consequently being the center of this data, then when we picked, even before we pick a sample, when we pick any sample, doesn't have to be our 0.7576, but any sample we have. So any sample we have is expected. Think about it as I'm writing this down. But when we pick a sample, then the high chance, if this claim truly is the truth, the true proportion of iPhone users out there, then anytime we picked up a sample, we already expect that it's expected that at 98% chance that because look at how big that common area is. The whole point is, at this claim value, center of the bell curve, any sample, even though being different from it, should be near it. Or, in other words, stays in the what we call the common area, the common zone. The zone where we can find values that are fluctuated up and down from the center, but common so that they can be allowed or accepted. And so, back to what I was about halfway saying here, any p hat that we picked up, any sample proportion value that we picked up, is expected at 98% probability to be in the common area. And again, being in a common area means the values can fluctuate up and down, but commonly found enough that they are allowed or accepted. So that's the expectation. That's the expectation before we pick any sample. But look at our sample. But no, reality just now showed that our real p hat equals 0.7576. Why is it that the only one sample, something that if I can pick one, somebody else can pick one similar like that, but this only one sample immediately, I have to use the word immediately because we can prove it. We have proven it. Is immediately in the unlikely area. That's the conflict right there. It's being in the unlikely, saying that it should be very unlikely to find a sample like this, but we found that so easy. The only one sample we picked up, we immediately ran into that. Versus, we expect to pick a sample that's supposedly inside of this, and the chance to be inside of this should be 98% chance. But now, the only one sample immediately falls into that right tail area. So that is the conflict I've been talking about. Because think about it, a lot of times if we're looking at a value, if the value is being the truthful value, then no matter how many times we pick samples, values will tend to be just fluctuating up and down, but small and commonly seen around the center. So the person who is making the claim here can defend as following, can defend himself or herself as following. Hey, even though I made a claim, but I am a human being, so I might be a little bit fluctuated. I might be a little bit fluctuating. So your sample being different from mine, but is that far enough to be considered as outside of the common zone, to be outside of the area where we commonly see other sample values being slightly up and down from my claim. And now we are going to answer that person. Yes, we already gave you a chance to defend yourself up to 98% chance, meaning we are already consider 98% chance, 98% of times when we pick sample, we should expect a sample value being in this area, but the only one sample we picked falls immediately in the unlikely area. That means the claim you made right here is a little too low. In other words, we have strong evidence now. That's how it makes p hat here. That's how it makes p hat strong evidence. To reject the claim, and the claim is h sub 0. So now that the claim P equals 0.3, the proportion of iPhone users is 30% in the world, has been rejected because that claim consequently became the center of all sample proportion values, and with our common area being up to 98% already. But unfortunately, the sample we found, 0.7576, is well into the unlikely area extremely to the right. And so think about a further impact like this. If the person made if the person, that same person who made this claim, made a different claim where the value was higher than 0.3. And so here it's getting a little abstract, but if that person right from the beginning made a claim value, a p value, a proportion value higher than 0.3, and I'm not going to appoint to any specific value anymore, but let's say just at some p being claimed but higher than 0.3. And of course that p being in the claim will become the center of the bell curve again. And from where and being the center of the bell curve, and from where our 98% here, if that claim is brought up higher so that inside of this 98% of the common area, our sample value being 0.7576 would fall inside of that common zone, then that's where we're saying that the sample is not showing strong evidence. Because now if the claim is brought up to a value higher where the 98% common zone being shifted along with that claim being higher because the common area is always that big fat area center at the claim, center around being around the center on the bell curve. So if that center is being shifted to the right, then keep shifting it to the right so that eventually when our p hat falls right into the common area right here, then at that point we're saying that this p hat is no longer is not strong evidence to reject the claim saying the proportion equals to this whatever being claimed here. But so why is that? Why is it that being in a common area, a sample falling in the common area is not showing strong evidence? Because that's where we can forgive. That's where it's acceptable. The person who made the claim is a human being. So the person can make a claim, and of course that claim will be fluctuated from all other samples. And just like how it says, we allow up to 98% of other sample values to be different from the claim. And now obviously if our sample here still belong to that common area, then that means nothing unlikely about the sample, nothing unusual about our sample here, nothing wrong with that. It's still somehow consistent with the claim because it's still, this sample is still belongs to the area where we commonly find values that's fluctuated from this claim in the center. And so that is the idea that promotes coming up with a alternative hypothesis, because once some H1s being rejected, somebody else bring up an alternative hypothesis so that we can keep bringing the claim higher so that eventually the sample we found here will fall into the common area or will no longer be the strong evidence to reject the claim any longer. And that's where we can now start saying that, hey, the new claim is going to be or can be accepted.